All right, so I have here the electric field due to charge ring. And I want to do some of these electric field problems with charge distributions and kind of build up to the electric field inside of a capacitor. And so we're going to start with the ring, and then I'll use the ring to do a disk, and then I'll do a disk to do a capacitor. I kind of like to also do this numerically, so I might do that in between just for fun to show you that it's the same thing. But let's just go ahead and get started. Let me go ahead and turn off this camera because I don't think it needs to be on. Okay, so here I have, let me move my microphone. So the situation is a ring in the XY plane, and I want to find the electric field along at some point on the z-axis. So there's a charged ring with a radius r and a total charge q. And we're looking at some observation location a distance z away. So just as a review, if I have some charge q right here, that's q, and it's at a location rq from the origin, and I want to find the electric field some other place, ro, the observation location, then I can find the vector r from the charge of the observation location. It's just the final position, ro, minus initial position, rq, and take the difference between those two. Then the electric field due to a point charge is 1 over 4 pi epsilon naught, that's just a constant, q over the magnitude of that distance squared times the unit vector r hat, because that unit vector is a unit vector point in the direction of r, so that would give an electric field in that same direction if that's a positive charge. If q is negative, it'd be going the other way. So we're all cool right there. But hopefully that's a review. Okay, so how are we going to do that here? This is the electric field for a point charge, and this is not a point charge. And the only way to do it is to break it into point charges. So we're going to break this ring into a whole bunch of little pieces and then find the electric field due to each piece and then add up all the electric fields. So let me just get a pen here, a different color. Let's say that I pick this piece right up here. That's a little charge piece, and I'm going to call that dq. That charge is going to make an electric field right here. And let's just sketch that out. So I'm going to put, this is the vector r. And that's a bad pen. That's the vector r. It's actually a vector. And that's going to make an electric field. If this is a positive ring, that's going to make an electric field going this way. And I'll call that dE. And that's a length r. And so I need to find, if I can find the electric field due to that little piece, it'd be all set. Okay. Now, one of the things before I do that, I could go ahead and say this. Let's just go ahead and write that down. dE equals 1 over 4 pi epsilon naught dq over the magnitude of r squared r hat. Now, as I go, I could find that. As I go around the ring, though, then r is going to change, and so dE is going to change. I have to add them all up, which is going to be done by integration. But before I do that, let's take advantage of the symmetry we have down here, because for every piece on the ring, there's another piece on the bottom down there. There's another piece, and that one's going to make an electric field like that. So every piece has a corresponding piece on the other side. And when I take these two electric field vectors and add them together, then let's call this the y direction. The y component is going to cancel. If they're over here and there, the x component is going to cancel. But the point is, the only component that survives is the z component. That's the only component that's going to survive if I'm on the z-axis. So actually, we can change this into a scalar equation. I can say dEz equals 1 over 4 pi epsilon naught dq over the magnitude of r squared. I don't need r hat because I've already included that, right? But I do need to find, if this is some angle theta, then the z component is just going to be the cosine times the dE. So I need to multiply this by cosine theta, because that's going to give me the z component. So that's my expression for the electric field due to each little piece. And no matter what piece I pick, anywhere around there, they all have that same expression. Okay? And what's great here is that no matter where I pick, theta is going to be the same. R is going to be, the magnitude of R is the same. It doesn't matter where I pick on the ring. So I can make this a pretty nice equation. So what I need to do is to convert all this stuff into something that I can integrate, right? Because dq and r, they're technically could change. I want to get this all in terms of z, because that's the parameter I want in here. So let's first get rid of, I don't think we need to get rid of dq. Let's just leave it. But I do want to get rid of r. So if this, let's look at the ring from the side. So here's my piece of my ring. This is a radius r. This is the observation location, so this is a distance z. And this is the lowercase r. So there you see I have a right triangle. So I can find r squared using the Pythagorean theorem. So r squared is going to be equal to big R squared plus z squared. I can put that in down there. What about cosine theta? Well, this is the angle theta. That's also the angle theta. And I could write cosine theta. Cosine is adjacent over hypotenuse. So it's going to be z over r. So cosine theta, I'll write it right here. It's going to be z over r. That's going to be equal to z over the square root of r squared plus z squared. So now I have an expression for cosine theta in terms of r, big R, which is constant, and z, which is a parameter I want. And I also have little r squared in terms of those. So let's put all that stuff together on a new page. So here I have dE z, the z component, 1 over 4 pi epsilon naught, dq, going to leave that there, that's a lowercase q, over r squared, which is going to be r squared plus z squared, times cosine theta, which is going to be the square root of, it's going to be z over, dEz is 1 over 4 pi epsilon naught, dq over r squared plus z squared, and then cosine theta was z over r, which is, I'm going to write this as r squared plus z squared to the 1/2. That's the square root. So now let's simplify this. And the only variable I have in this integration as I add up around the ring is dq. That's the only thing that changes. Okay. So this is a constant parameter that I want out of the calculation. And r is the radius of the ring. So I get dE z 1 over 4 pi epsilon naught. Now I have z, and then I have r squared plus z squared times r squared plus z squared to the 1/2. So that's going to be r squared plus z squared to the 3/2. And then I have dq. Now I need to find the total electric field. So that means I need to add up all the components of the electric field in the z direction. So that's an integration, and I need to integrate this over q. I need to add this up over all q. So if I add up all the little dq's over the ring, I just get q. So this is just going to mean that the electric field in the z direction is going to be 1 over 4 pi epsilon naught zq over r squared plus z squared to the 3/2. Okay, now let's check this. We need to check the units. We need to check as z goes to infinity, and then also check as z goes to 0. Let's check those values. So first the units. If you remember, I have the electric field due to a point charge is equal to 1 over 4 pi epsilon naught q over r squared r hat. So I need the 1 over 4 pi epsilon naught. I got that. I need the charge over distance squared. So is this charge over distance squared? So I have charge, and then here I have, this is going to be units of distance squared times to the 3/2 is going to be distance cubed, but then I have distance on the top. So I have meters over meters cubed, so I do get the right units. Okay, what about as z goes to infinity? Well, a couple things should happen, right? We can actually I have another one. As r goes to 0. So as z goes to infinity, the electric field should go to 0, right? Because I have a finite charge distribution. These are all individual point charges. As I get really far away, the value of the electric field should go to 0. So if I let z go to 0, then I have 0 over 0. Now, I'm going to skip this step because I don't want to spend too much time. But what happens then is we can... No, I don't have 0 over 0. Because on the bottom, I get... as z goes to infinity. I get infinity over infinity. So what you can do is to take the derivative of both the top and the bottom. Use L'Hopital's rule to find the limit as this goes to infinity. And you'll find that on the top, you're going to get q. On the bottom, you're going to get a z term still. So you're going to get 1 over infinity, which does go to 0. So that checks. Now, what about as z goes to 0? Now, it doesn't really matter what the value is as long as it doesn't explode. Well, it could explode. It does for a point charge. But if you think about this, in the middle of a circle, this piece is going to make an electric field going down. This piece is going to make an electric field going straight up in the plane of the circle, so it should cancel. So I should have a 0 electric field in the center of as z equals 0. So if I put z equals 0, I have 0 on the top, I have r squared, r cubed on the bottom, I get 0. Finally, what if I let my ring get really, really, really tiny? Then it should look like a point charge. So if I let r go to 0, I get z over z cubed, and I get q over r squared, q over z squared. So that works too. So this looks like a good equation. The one thing that we could do is to plot this. That might be kind of fun. Let's see, how long is this? 12 minutes? I want to do it. I'm going to do it anyway. Okay, let's just plot the electric field as a function of z for some values. I'm going to pick a charge of 1 nanocoulomb with a ring size of r equals, I'm going to say a centimeter, 0.01. So that's all I need. And then I can plot this from z equals negative 0.05 centimeters to positive 0.05 centimeters. And let's just do that. I'm sorry, that's meters. Okay, so let's switch over here to the computer. I mean, that's why I have this whole thing set up, right? So I already have Python set up. I'm going to need, let's go ahead and put in my constants. K equals 9 times 10 to the 9th. That's set. K I'm calling it as 1 over 4 pi epsilon naught because I don't want to write 1 over 4 pi epsilon naught when I'm writing a computer program. Q is, I said 1 nanocoulomb, 1 times 10 to the negative 9th. And then R was equal to 0.01, 1 centimeter. Now let's make a graph. T graph equals graph. Let's give it a title. Title equals EZ due to ring. That looks good. Let's give it an X title equals Z in meters. And then a Y title. And that's going to be EZ, the Z component of the electric field in newtons per meter. Newtons per coulomb, sorry. Okay, that's good. Now I need the curve, so let's call this F1 equals G curve color equals color.blue. I always make it blue, and I don't even know why. Now what I need to do is to, I could make a function to calculate the electric field, but it's just one equation, so it shouldn't be too bad. But I do need to pick my value of Z. So I'm going to say Z equals negative 0.05, and I need my step size. So let's say DZ equals 0.001. Let's just try that. We can make it smaller if we want to. Now I'm going to say while Z is less than 0.05, right? So I'm going to take my z value, I'm going to calculate the electric field, I'm going to plot it, and then I'm going to move my z value up to the next place and do it again. So the first thing I'm going to do is to calculate the electric field. So let's just say Ez equals, now I'm just going to type my formula here, looking at my paper, make sure I don't get it wrong. So I have 1 over 4 pi epsilon naught, that's k, times z times q divided by r squared, squared in Python is star star, plus z squared raised to the 3/2. That's my electric field. And as z changes, that electric field z component is going to change also. So now let's plot that, f1.plot z ez, and then let's update, let's move our z value, z equals z plus dz. And this should work. I didn't save it. Ez due to ring. I like ez. This seems like it's too easy, but I feel like I'm missing something. Well, I'm not missing something. Check that out. Okay, that's exactly what you want. So actually I think it's a little jagged there. So let's make this a little bit smaller. 0, 2. Yeah, that looks nice. Very nice. So here's my electric field. As it gets really far away, it goes to 0. At z equals 0, it goes to 0. That's good. You notice here the maximum electric field is some distance away, right? That's because if you get too close, the components start to cancel. If you get too far away, then you're too far away from the point charges. So that's a nice little thing right there. We could plot in here the electric field due to a point charge of the same value. Let's do that just for fun. So let's say f2 equals g curve. Now I'm going to have to do something here. Color equals color dot red. I guess I could give this a label. Nah, I can tell you the label. Now what I'm going to have to do is I can't plot this from, I can't go from z equals 0 because the electric field due to a point charge at z at the origin would be infinite. So let's just jump down here to this value right here, which is x equals 0.0. What's that? 0.002? 0.02, 2 centimeters. So let's say I'm going to go back over here. I'm going to say z equals 0.02 centimeters, and then I'm going to say while z is less than, let's do this a little bit larger, 0.07, and let's just change this one too. So now I need to calculate the electric field due to a point charge. I'm going to say Ez equals, it's a new Ez, Ez2, I guess I should say, k times q divided by z squared. And I'm going to plot that, f2.plot z Ez2, update z equals z plus dz, and run it. And you'll see here, that's pretty good. I like that. You'll notice that as you get closer and closer to the ring, the electric field due to the ring and the electric field due to a point charge with the same charge diverge. But as you get further away, they pretty much agree. So over here, I'm at x equals, almost 4 centimeters away from the ring of a 1 centimeter radius ring, and there's not much difference between the point charge and the electric field due to a ring. So, and this is on the z-axis. Now, the real question is, what if, let me switch over here to the paper again. What if we're not on the axis? So let's just draw this from the side. Here's my z component, z direction. Here's the side view of my ring of radius r. What if I want to find the electric field right here? RO. Well, then I got a problem. Because all the things that I did before, the electric field due to this one would be this way, DE1. Down here, the electric field is going to be that way, DE2. And they don't cancel. Okay, so I can't get any nice symmetry as I integrate around. Also, this R and this R R1 and R2, are both different magnitude and different direction. So this is a problem that's not really something you could set up as an integral, but we can do it numerically. And I am going to do this numerically because why the heck not? Okay, and no one can stop me. So I'm going to do this by breaking this into a finite number of points and just actually adding up the electric fields. Okay, but that's where we'll pick up on the next video.